Okay, classes are canceled due to snow, so you take advantage of the extra time to conduct some physics experiments. You fasten a large toy rocket to the back of the sled and take the modified sled to a large, flat, snowy field. You ignite the rocket and observe that the sled accelerates from rest in the forward direction at a rate of 13.5 meters per second squared for a time period of 3.30 seconds. After this time period, the rocket abruptly shuts off, and the sled subsequently undergoes a constant backward acceleration due to friction of 5.15 meters per second squared. Part A, so we'll say that explicitly. Part A, after the rocket turns off, how much time does it take for the sled to come to rest? And then part B, by the time the sled finally comes to rest, how far has it traveled from its starting point? That's those two things. Physics problems are easier if you draw a decent and well-labeled picture. So here's my snowy field, and here is the sled. It starts at rest, so v equals 0. The rocket accelerates it forward with something I'm going to call a sub 0, and then that happens during some time. So my times are going to be t equals 0 here, and then t equals t1 here. Then the rocket shuts off, and the thing comes to rest again. So back to rest at a time which is tf, because there was an acceleration this way of magnitude a1. Now I know some of these values. I know a lot of these values actually. For instance, I know that t1 is the 3.30 seconds. And I know that A0 is the 13.5 meters per second square. And that A1 is the 5.15 meters per second square. Notice that I have it as plus here, even though it's a backward acceleration, because I've taken care of the backwards with the arrow. And as such, I don't have to put it into the value there. That means later on, when we want to translate what our acceleration is, we'll say our acceleration is minus A1. Right? And then for some other pointers or references, we're going to put our axis, we're going to put the origin where the rocket starts. I'm going to say the plus direction is the direction the thing actually moves. We're going to say that when the rocket cuts off, it has a speed, which I'm going to call v1, that I don't know. And then I'm going to also say that it starts at the origin, sort of duh. We're going to call where the rocket shuts off is going to be called x1, and where the rocket stops finally is going to be called xf. So that is our well-drawn diagram. Now we just have to do stuff with it. Okay, part A. Find the time, which I'm going to call delta t. So here to here, that's delta t. We want to find delta t. We don't want to find tf per se, because they ask us for the time it takes after the rocket shuts off. And I can go to my friend the least helpful genie. I say, least helpful genie, grant me one wish, and what I'd like to know is the time. But the genie is very unhelpful. In fact, it's the least helpful. And so it says, no, what else could you know that would help you find the time? So I look back at this problem, and I say, well, I have constant acceleration case, and I have an initial speed, and I have a final speed. If I knew this initial speed, and I had the acceleration, and I have a final speed, I could get the time, because I could go through something like the following equation. I could say that the final speed is that initial speed plus the acceleration times the amount of time during which the acceleration occurs. And this acceleration here would be minus a1. Sadly, while I do have the final velocity, which is 0, and I do have the acceleration, I don't have this one. So I need to get that, which is a little frustrating. But not too bad, because I can look back over here and I say, well, Genie, get me that velocity. And it says, no. What would you need to get that velocity? Well, since I have a constant acceleration to start, and I have a time during that acceleration, this is 3 point whatever seconds, given the initial velocity and the time and the acceleration, I would be able to get the velocity. In fact, I don't need the Genie anymore. I can say something like the following, that v1 is also the initial plus the acceleration during the first part times the time of the first part. And we know the v initial is 0. So v1 is simply A0T1. Sorry. We could actually get those numbers, because after all, we have A0 and we have T1. And I'm not going to, because I don't want V1. I just want delta T. So I'm going to leave out numbers until I actually have to put them in case I can simplify stuff. The important thing is that I have, or know that I have, that number, so I could get it if I end up needing it later on. All right. Once I have that, I can go back to my other equation. I can take this stuff and plug it in here. I've got a little complicated here, but that's okay. So this equation becomes, sorry, 0 is A0T1 minus A1 delta T, because we know that we end at rest. And that equation can be solved. Now I really do have a bit of a mess, but not too bad. So I'm going to take this equation. I'm going to go to a new page to solve it, but it's kind of trivial. So where we are is we have the equation 0 equals A0T1 minus A1 delta T. There's a lot of symbols going on here, so I want you to remember where this comes from. This is just as the final velocity is always the initial velocity plus the acceleration times the time. The final velocity is 0, right? We know it comes at rest. The initial velocity we found from the first part of the problem turns out to be the acceleration times the time of the first part of the problem. So this is really the initial velocity at the start of the second part of the problem. And then the acceleration here has a minus sign because it's pointing leftward, and I have to respect that minus. Then it is just a matter of just doing some algebra. So for instance, I want to isolate delta t, and the first thing is to get everything with delta t by itself. And so I'm going to add A1 delta t over here. But there's only one rule in algebra, which is whatever you do on one side, you have to do on the other side. So I add it over here. That gives me a new equation, A1 delta t equals A0 T1. And then I want to isolate delta t, so I divide by A1. But I have to do it on the other side as well to keep the balance. So that now my equation becomes simply delta t is A0 over A1 T1, which for our numbers were 13.5 meters per second squared over 5.15 meters per second squared. Times the initial time, which was given as 3.3. Seconds. And when we grind all of those numbers out, we end up with, on the calculator it says 8.650485437, which clearly rounds to something like 8.65, which does accord with what Sapling told us. So at least we're in the same place there. All right, part B says find XF. That is the total distance from when the rocket ignites to when the whole thing comes back to rest. And again, this is really the junction of two different things, because stuff happens here where during this first part we have acceleration to the rightward but constant, and during this part we have acceleration to the left but constant, and so they are two constant acceleration cases. I'm going to solve this two different ways. I'm going to solve it algebraically, and then I'll go back and solve it graphically. You can use the graphic method a lot, and is often faster because we've accidentally gotten some information along the way. But to solve this in either case, what I need to do is figure out two different motions, because I need to figure out separately how far does it travel during this portion, but I have to know where did it start. So I also need to find x1, or how far it traveled during this motion. So I'm going to get the first bit first. I'm going to say that during the first motion, I have that x is x initial plus v initial times the t plus 1/2 times the acceleration times t square. And for us, this ends up being that, therefore, x1 is 0 plus 0t, yay for that, plus 1/2 times the acceleration, which was a0 times t1 squared. So in the end, the position is 1/2 A0T1 squared. And before I go any further, I do want to kind of emphasize that this thing, starting from rest with constant acceleration and moving for some time, this kind of thing is going to show up a lot. So I wouldn't memorize it, but get used to seeing that the distance traveled is a half times the acceleration times time squared. It shows up a lot. All right, if we go over to the other side of the wall, then we have something similar. We have that the delta x is going to be v1 delta t plus 1/2 times the acceleration, which was minus a1, times delta t squared. So we're going to have v1 delta t minus 1/2 a delta t squared. And then we could throw in numbers at this point, and it would probably be the easiest. So I'm going to have to take the velocity was the acceleration 0 times t1, now also times delta t, minus 1/2 times a times delta t squared. Okay, it's getting a little cramped in here, so I'm going to try and get this to write this out correctly. We'll see. The A0 was 13.5 meters per second square, and T1 is 3.30 seconds, and delta T is 8.65 seconds. That's that top term, and then I'm going to subtract off 1/2 times, and it's 5.15 meters per second square times 8.65 seconds quantity squared, and throw that into my calculator to get an answer, which I have to sort of put over to the side here, is going to be, well, let's just write it here. It's going to be 13.5 times 3.3 times 8.65, subtracting 1/2 times 5.15 times 8.65 squared, and we get something like 192 meters. This is 192.69 meters. I didn't get x1, so I should do that as well. x1 is going to be 1/2 times 13.5 times 3.3 squared. So x1 is 73.51 meters. But I need them together, so I take that and I add in the 192.69. I get something like 266. I really ran out of space here, so I have to do that on the page. All right, we'll do the sum at the end here. So the actual position xf, where I end up, is where I start plus how much extra I get. Sort of the h here. So I add 73.51 to 192.69, and I end up with 266.195, and if I say figs, sampling says that should round to 266, which is the agreement with sampling. So that's one way to do that. Part B could be done graphically, since we have some stuff here, and I'm going to do that next. But it's going to be the same answers, of course, because it's the same thing. I'm going to need the actual speed v1, which I have so far avoided finding, but you might remember from way back when that v1 was A0T1, which if we put in our numbers, 13.5 times 3.3, the initial speed was 44.55 meters per second. I'm going to use that because I'm going to go back to the idea of these two problems here, and I'm going to solve them both graphically by saying I have dt, and at first the rocket has some large acceleration, and at 3.3 seconds it has reached 44.855 meters per second. And then in the second case, we end up, let's have our velocity graph look something like this, and our initial speed will be 44.55 in meters per second, of course, with an axis of v versus t. But now it's going to slope downward more gradually, and we learned that that was 8.65 seconds. Which makes life relatively easy, because what we want are the two distances, and the distances would be these triangles. So x1, which is the displacement in the first case, is just 1/2 times 3.3 seconds times 44.55 seconds, which is 1/2 times 3.3 times 44.55 is 73.5 meters. And then delta x, which is going to be this area, is going to be 1/2 times 44.55 meters per second times 8.65 seconds is 192.68. And when we add 192.68 to 73.5, we get to 266 again. So XF is still 266 meters, as expected. It certainly looks like the graphical method is faster, and it's fine to use that. You should really be fluent with both of them, because sometimes we'll need to manipulate the equations, and it won't be convenient or easy to get. But you can do it either way for a problem like this.